Good morning, sir.
Good morning,
sir.
Amit.
कैसे
Good
हैं, sir?
morning. How are you?
Fine, sir.
Congratulations for this excellent workshop.
Thank you, sir. आपका support मिलता रहता है.
बिल्कुल.
सर शुरू करें.
हाँ.
Once again, on the last day of our FDP, I welcome all the participants and Dr. Hemant Kaushik, sir. Dr. Hemant Kaushik, sir, is presently working as a professor in Department of Civil Engineering at IIT Guwahati. Along with that, he has additional responsibilities of Head Center for Educational Technology and Associate Dean Academic Affairs. He was awarded with Fellow of Institution of Engineers since 2020, David Fischett Award for his research work in 2019, INA Young Engineer Award in 2010. He has professional membership of Earthquake Engineering Sectional Committee, CED, Board of Bureau of Indian Standards, ED USA, the Masonry Society USA, Indian Society of Earthquake Technology, India, Institution of Engineers, India. His research interests are earthquake and recent design of structures, nonlinear behavior of structures, retrofitting of structures, seismic vulnerability assessment of structures, and earthquake damage surveys. So, and many more awards he has won. So now I request sir to enlighten all of us for his lecture.
Thank you, Amit. And, let me share my screen. And I think I can switch off my camera to reduce the bandwidth. And how much time do I have, Amit? You are muted.
Sir, 11:30.
Okay, fine. So is it visible?
Yes, sir.
Okay. So a very good morning to all the participants, faculty members, students, and staff members. I first thank Dr. Amit Sharma and his colleagues and the Institute for inviting me in this very interesting faculty development program on new approaches in geotechnical earthquake engineering. So today's topic that I've chosen is not really related to the geotechnical earthquake engineering, but the application of geotechnical earthquake engineering is in the ground motion seismic models, the ground motion simulations. So those applications we will discuss today. So we'll see what are the influences of these ground motions on the seismic response, particularly the seismic fragility of structures. So the first question that came to our mind is, why do we study this? Why are we so bothered about the influence of these ground motions on the structures? The first thing is, every ground motion is unique in the sense that whatever ground motion record you have, you just compare it with any other ground motion record that is available anywhere, and you will never find that two ground motions are, forget about exact similarity, they are not even approximately similar. They are unique in nature. All the characteristics are unique. So the next question is, then how can we analyze the structure for just one ground motion? It is simply not possible. Okay, so we have to use several ground motions so that we can find out the demand on the structure, considering the influence of all these ground motions, and the most critical demand we have to use in design of the structure. So that is also very tricky, because there are thousands of ground motions available So how many ground motions we should consider? And then which type of ground motions we should consider? Because there are near pulse ground motions, near fault ground motions, then there are far field ground motions, there are intermediate ground motions, deep earthquake, shallow focus earthquakes, right? So many ground motions are available. So we have to first study what is the influence when we use different ground motion parameters. So what is their influence on the structural performance? And that we have to study. Only then we'll be able to answer these questions. So if we carry out this study, what are the applications? What is the use of such a study? So these 5 applications I have noted down here. There are many more, but I will discuss these 5 applications in brief. If we want, we can have full 5-day faculty development program on each of these applications, right? So I'm telling you just to let you know that I'll be discussing each of them very briefly. I'll try to cover within 1 hour 15 minutes. So this is very brief, but we can have very detailed discussion in each of these applications. So first application that we will discuss is the seismic performance assessment of the structures. So we have to, whenever we want to assess the present seismic condition of the structure, we have to carry out different types of analysis. One of those is the time history analysis, nonlinear time history or nonlinear dynamic analysis, where we need to consider these ground motions. So that is first application. All these questions that I have asked these 4 questions, we have to use them in these applications, use their answers. The second is evaluation of effective engineering demand parameters to predict the failure. Now, what are these engineering demand parameters? We will discuss in detail, but for time being, any parameter, any demand parameter that can be used to study the structure, to find out the response of the structure, is an engineering demand parameter. For example, the top displacement of a structure. Let's say there is a 4-story building. When we do pushover analysis or any analysis, we can measure the displacement at any point of the structure. So that displacement is one of the engineering demand parameters, right? The bending moment in the column, the shear force in the column, or any other deflection in the, and so any parameter, any demand parameter, it can be used in the analysis. But what is the most effective engineering demand parameter that can be used to predict the failure? So this study requires a lot of input from ground motion side. Okay. Third is the sensitivity analysis of the input parameters that can affect the seismic performance. Now, these input parameters can be anything. It can be width of column, it can be grade of concrete, it can be live load acting on the slab. So there are so many input parameters that we are required to give to the software to do the analysis. Unless we know how sensitive is the output of the structure to these input parameters, we will not be able to carry out a proper analysis. So you'll understand more about it when we go into detail. So that is the third application. Fourth is the estimation of uncertainties. So there are so many uncertainties whenever we carry out nonlinear or even linear analysis. So if you want to estimate the real uncertainties in these seismic demand arising from various sources, then we have to carry out this analysis considering the ground motions. And finally, of course, the seismic fragility. If you want to find out, we have to do this detailed analysis. So what we will do is studying each one of them in a brief. So first I'll tell you what are the input properties that I will be considering in this study. So these input properties remain the same for all the 5 applications. So this is a 4-story reinforced concrete frame that I'm considering. Now this frame is here, the middle frame of a multi-story building. So I'm analyzing only this frame. And these are the dimensions of the building, the dimensions and reinforcement detailing of the columns and the beams. So I'm considering three configurations of this frame. The first configuration is fully infilled frame. The second configuration is the open ground story frame, where we don't have the masonry walls in the ground floor. So these are the OGS frame. These bare frames are the BF frames. And these are the fully infilled frames, so FI frame. And these are the bare frames, BF frames. So here we don't have any infill walls. And in each of these frames, what I'm doing is I'm changing. So this is a basic frame, right? So here I'm changing the number of bays from 1 to 6. I'm changing the number of stories from 2 to 6. I'm considering the opening in the wall right from 0% to 90%. So 0% opening means it is perfectly solid, no opening at all. 90% means it is more or less fully open here, or any story, right? So this is the variation in the opening percentage. And the peak ground acceleration variation I'm considering from 0.1 g, which is very less, to 1 g, which is very high. So these are the variations I'll be considering in all these studies. The lump plasticity model will be considered in the nonlinear analysis, and the masonry infill will be modeled using the equivalent diagonal strut. And then there are some equations that were used for estimation of the length of plastic hinges, and how to model the equivalent diagonal strut in case of openings in the wall. So that a past study has been used to modify the parameters, the properties. Right. So if you have to carry out the seismic performance assessment, there are many methods. One of them is nonlinear dynamic analysis, where we use these ground motions. So I will be considering all three types of frames and then consider the material model for concrete. Now you can see here the material model is the cyclic degradation model, because we are using the dynamic analysis, the cyclic nonlinear dynamic analysis. For steel, this is the material model. Of course, you have to provide the details for the degradation in the material. And for the masonry infill, right? This is also cyclic with degradation curves. So once we have these material models, we have to then consider the ground motions. So these are some of the ground motions that we need. And then we have to carry out some finite element sensitivity analysis. So just to understand what kind of refinement, what kind of mesh size, how many elements we have to use. So considering all these together, we can carry out the dynamic analysis, and we get such kind of output where we are here plotting the peak interstory drifts. Just for example, so we are plotting the interstory drift along the height of the frame, right? For three different frames: bare frame, open ground story frame, and the fully infilled. If you have any questions, you can stop me in between. Don't worry. I'll be happy to answer on that slide itself. And of course, you can ask me in the end too. Right. So these are the 7 original ground motions that I have considered in this study. Right. So, I mean, this is 1940 El Centro, very old earthquake, but it is the most commonly used ground motion in any of the nonlinear dynamic analysis. And up to 1999 Dutch earthquake I have used. So these are different parameters or characteristics of the ground motions, and you can see how different they are. So what I've done here is I'm plotting the energy density curves, and these are the normalized energy density curves for all these ground motions. So you can see how different these are, right? And those of you who are not familiar with the energy density, you must be knowing the response spectrum. So here are the response spectrum that is calculated or plotted for each of these 7 ground motions, right? So they're completely different. So consider, for example, this double line earthquake, which is Tabas earthquake, and compare it with this small dotted line earthquake, which is El Centro. So much of difference in the ground motions. So what I've done here, these red lines, they denote the natural period of vibration of these 3 frames. So bare frame is here, open ground story frame is here, and the fully infill frame is here. Right? So now you can imagine if you have to design open ground story building or even a bare frame building, and you are using this ground motion, which is Kobe, versus you are using this ground motion, which is either Indo-Burma or Dutch earthquake. So if you use these 2 earthquakes, look at how different output will be. The pseudospectral acceleration for this will be about 0.15 G, and for this earthquake, which is um, Kobe earthquake, you will get about 1.75 G. That is the difference we are talking about, right? So initially when I said that you cannot do this analysis for just one ground motion, now you tell me which ground motion will you use to do the analysis when you have so much of variation in the seismic demand. So that is the problem that we'll try to address today. And then for each of these ground motions, these 7 ground motions are the original ground motions. Now what we did for each of these ground motions, we varied the peak ground acceleration from 0.1 G to 1 G in an interval of 0.05 G. So you get 20 more ground motions for each ground motion. Okay. And then further, we have actually developed some frequency envelope dependent samples of these ground motions. So for each of these, for example, El Centro is shown here. We know what is the frequency here. The dominant frequency for El Centro is 9.2 radians per second. So keeping that frequency roughly similar but with minor variations in that frequency, so we developed this frequency envelope dependent sample. 16 samples were further developed to understand if there is any change in the demand on the structure, even if there is a small marginal difference in the dominant frequency. So now you can imagine how many analyses were carried out, and we'll discuss more about this. So this is a very simplistic output of some of these analyses. So what I'm doing here, I'm comparing the nonlinear static pushover analysis response of the structure with the response I got from the nonlinear dynamic analysis. So this is nonlinear dynamic analysis, and I'm trying to compare. So this capacity curve coming from the static analysis, nonlinear static pushover analysis, you can get directly as an output, but this curve you will not get directly. So this is the derived curve from the output, from the base shear, that is from the base reactions that are available, and the top displacement. So just to let you know that we validated the results with the nonlinear static analysis also, and there are more or less matching, but the difference here was expected. The pushover analysis will always give you more results in case of stiffer frames, and that is very obviously displayed here. Now we'll use all these input properties, all these observations in the second part of the study, which is the evaluation of effective engineering demand parameters. Now the question is, why do we need this? Why we cannot simply use the top story displacement as the engineering demand parameters? And let me inform you that 99% of the studies, they use the top story displacement as the engineering demand parameter, because that is the most easiest demand parameter to obtain. Now let us see what happens when we do that. So what I'm showing you here is the open ground story building, which is irregular, vertically irregular building. And we will use some of the local EDP and the global EDP in these buildings. So we know what is the problem with the open ground story, right? The ground floor columns, they are subjected to very heavy ductility demand, very heavy shear demand. And most of the times these ground floor columns, they fail. And what we see is very interesting that most of the lateral deformations, they are accumulated in the ground floor during earthquake, and the upper floors are more or less undamaged and they remain vertical. Okay. So there's no relative deformation in the upper stories of the open ground story frame. All the relative deformation is they're accumulated here in the ground floor only because it is so soft. So that means that the entire capacity of this building or these frames, it is controlled by this one floor only, the ground floor only. It is not dependent on this except for the mass, right? So in such a situation, what happens? So what we will do, we will compare the local to global deformations in these open ground story buildings, considering some the points which are generally taken on the force deformation envelope curves, right? So, for example, if I show you here the nonlinear static pushover curve, this is immediate occupancy level, this is life safety level, and this is the collapse prevention level. So you can see even in immediate occupancy level, we have some damage to these ground floor columns which are open, but no collapse, but slowly it enters into the failure also, right? So we'll consider these types of failure modes. And this is what I was mentioning, that when you apply a lateral load at the top, the lateral deformation of the open ground story frame is such that you have huge accumulation of lateral, all these deformations here only. And the vertical upper floors, they don't generally deform much. So what we did, we consider the mean sampled frames. I'll let you know later what are these mean sampled frames. Mean means all the material values, all the geometry values, all the loading values were considered mean. So there was no variation in the properties as far as the geometry is concerned, as far as the material is concerned, and as far as the loading is concerned. But there are huge variations in the ground motion parameters. So we consider these 7 ground motions and we scaled them for 25 different PGAs. So we carried out 525 nonlinear time history analysis runs. And so these results are the output of this 525 nonlinear dynamic analysis. So in the first instance, we considered the maximum top level displacement as the engineering demand parameter, right? So if you look at this figure, so this displacement only. So this displacement I'm considering as the engineering demand parameter. So considering that displacement, I'm plotting here the relative displacement along the height of the building. So this first story, second story, third story, and fourth story. And you can see here, I'm comparing these bare frame deformations with the open ground story frame deformations. Okay, as obviously we discussed already, the open ground story, most of the deformation is accumulated in the first story only, and the upper stories are vertical. They remain undamaged, and more or less there's not much deformation there. But the bare frame, they deform gradually from bottom to top. Now, if we consider the top level displacement as the engineering demand parameter, it is very obvious here that the bare frames are subjected to higher demands, right? So that means you will then think that the bare frames are more vulnerable because demands are more. But that is not true, right? We know that open ground story frames, they are more vulnerable. They are more risky. So if we compare the full infill frame with the OGS frame, we get these kinds of results. Even for some cases, you see the full infill frame also behave more or less like open ground story frame once the ground floor infill is failed. So one thing is clear here, that the top level displacement cannot be considered as a critical displacement or the engineering demand parameter for the open ground story frames. It is simply not possible, because the kind of output that we are getting, because the relative deformations here, it tells the story that we cannot use it. Now, this study was carried out for only one or maybe three peak ground, four peak ground accelerations: 0.3G, 0.5G, 0.7G, and 1G. But if we consider the full variation in the peak ground acceleration, right from 0 to 2G, then a very interesting picture come to mind. See, here you see all the three plots are for the bare frame, top level displacement, open ground story frame, top level displacement, and fully infill frame, top level displacement. So what you see here is that the bare frame, of course, is having the maximum demand, right? Then it is followed by the open ground story and finally the fully infilled. This is not correct. This is not the real behavior of the structure. Now, if I plot the ground level displacement, then what you get is that open ground story frame has the maximum demand, followed by the bare frame and the fully infilled frame, right? So this is more realistic. It appears to be more realistic. But then mind you that this ground level displacement we are considering from the same results, right? This is not the different analysis. The analysis remains the same. Now, let us consider a different engineering demand parameter. So here I am considering maximum interstory drift as the engineering demand parameter. So look at the output. If we consider the bare frame versus the open ground story frame, these are the kinds of output we are getting. So even in case of maximum interstory drift, so here it means that the first story interstory drift we are plotting is the second floor interstory drift and third floor. So obviously you will find that above second floor there is no interstory drift in case of open ground story frame, because all the deformations are accumulated here. In case of bare frame, you always have gradual displacement from bottom to top, and these are the variations, the relative displacement variations, which are actually the drift across the height. So this appears to be a better model, because in every case you will get the demand more in case of open ground story, right? Even if you compare the fully infilled with the open ground story, the same story is there. So this is only for the L centro ground motions. So obviously these results show that the ground floor columns are subjected to very high ductility demand. And we need to have this component level demand to capture the failure. Otherwise we'll not be able to capture the failure. We'll not be able to find out the real vulnerability. So if we now compare across the PGL level, the same ISD as the EDP, a very different picture emerges here. So again, you will get that across the PGL level, you again have this bare frame demand more. If you consider the top story interstory drift, right? If you look at here, after second floor, you have this more, right? So bare frame is more vulnerable in that case after second floor. So this is what is happening here. This is followed by the fully infilled frame, which is the red dots, and the open ground story frames, which are these dotted lines, right? And if you compare the ground level, the story is completely changed. So again, you will get that open ground story has the highest demand, followed by the bare frame and the fully infilled frame, right? So obviously, we cannot use top story displacement to design the open ground story frames, or even to assess the open ground story frame. Now, if you compare the degradation in the stiffness, when the damage occurs in the building degrades. So let us compare that degradation by finding out the stiffness factor, which is a ratio of base shear to displacement at different levels. And it is normalized with respect to the maximum top level stiffness. So when we do that, you can see very easily here that for open ground story frame, there is no difference at all when we find the stiffness factor for the top level and for the ground level. But for the bare frame, there is a difference. For full infill frame, there is a difference. So this clearly shows that open ground story buildings, they have no influence whatsoever coming from the top level displacement. It is only the ground level displacement that is influencing factor here. But in case of bare frame, of course, there is a huge difference between top level and ground level displacement, and in fully infill frame also. So this again validates our observations. So then we can compare various engineering demand parameters similarly. So we have compared the peak top level. We can compare the story displacement corresponding to peak top level displacement, and then the interstory drift at top level. We have already considered that, and the interstory drift at the ground level. And if we find out the seismic fragility, we get these kinds of results for different ground motions. So these are the damage states. So for different damage states, we get the seismic fragilities, and these fragilities shown on the vertical axis here. So for slight damage, for moderate damage, for extensive damage, and for collapse, we get such kind of fragilities. So this blue shaded, not blue, but only the shaded bar charts, they represent the bare frame, and the filled bar charts, they represent the open ground story. So you can see here that there is no definite pattern, right? In some cases, the bare frame fragility is more. In some cases, the open ground story fragility is more. Even in case of comparison between fully infilled and the open ground story, same situation is there, right? So what I want to show here is that the fragility estimation with top level displacement as EDP gives the wrong essence of the physical behavior or the failure pattern of irregular open ground story frames under the effect of seismic input. It is not a proper EDP to use. If you use the story displacement corresponding to peak top level displacement, so again we are using peak top level displacement, but we, instead of using that as EDP for that top level displacement, we are using corresponding story level displacement as EDP. So you can find here that this is a much better version to use. But still, it is not realistic. It still does not show the exact behavior of the system. So these red lines, red solid lines, they represent the open ground story. The dotted line here are bare frames, and the dotted line here are the fully infill frames. So for collapse condition, you can get that open ground story buildings have higher fragility, right? But then even for the moderate earthquake or for the extreme level, even extreme level, you have more or less similar kind of fragility as far as the higher PGAs are concerned. For low PGA values, the OGS fragility is more. But in this case, slight and moderate, even for them, the seismic fragilities are more or less matching. And same is the condition here. So again, this EDP also does not reflect the realistic damage. We should not use this EDP as well. So third EDP, if we use the interstory drift at each floor level as EDP, then we get this kind of behavior. So this story-wise distribution of the fragility for bare frame, for one peak ground acceleration, this for OGS, and this for fully infilled. So again, same story, right? For each floor level, if you use, then it's of not much use actually, because the behavior is more or less similar in all three cases. And here also you will find these are the fragilities for this interstory drift at top level as EDP. So you can find that the seismic fragility of the top story columns is almost nil. See, we are talking about top story here. So for the OGS, the solid filled boxes, the bar charts, they're almost not there, right? So then the seismic fragility, that means it is very less, almost nil, compared to the bare frame or to the open or to the fully infilled frame. Okay, again, not realistic here. And basically, we are not worried about these top story columns in case of OGS because we know these columns, they don't fail. Now, in contrast, if we use the interstory drift at the ground story, then the complete picture changes actually. Now you can see that these solid boxes are always higher. These bar charts are always higher compared to the bare frame as well as the fully infilled frame. This clearly shows, for example, look at here. This is the fully infilled frame, the shaded bar chart, bar, and this is the open ground story. How different seismic fragility is for each of these cases. Now, this is realistic. We see that fully infilled frames during earthquakes, they don't collapse. The frame still can collapse if the ground floor infill is failed. In case of this also, you can see this is the shaded one, this is the solid one. So there's a tremendous difference. In all cases, the seismic fragility of open ground story buildings is much higher than the bare frame or the fully infilled. This clearly shows that if we use the component level demand parameter. So component level means the interstory drift at the ground story level. This is the component. Then it is more realistic rather than using the conventional method of using roof displacement as the EDP. Right? So it is, and this is particularly true for irregular frame behavior. For regular frames, we discussed that bare frame is a regular frame. For that, the top story displacement is okay. For fully infilled frame, again, which is regular, the top story displacement is fine. But for irregular frames, it is not capable actually. Right, so that part of the study is over. We have found out what is the engineering demand parameter, the best engineering demand parameter or better engineering demand parameter. And you found how many analyses were required, what kind of ground motions, how many ground motions, right? So although I'm not showing you the the individual responses from those analyses, but around 525 nonlinear dynamic analysis were carried out to get these kinds of output. You can see here, this is just output coming from one ground motion for one damage state. And so many damage states here, so many earthquakes, right? Takes a lot of time. The next part of study is estimating the sensitivity for these random input parameters. So we need this sensitivity analysis in the next stage also for evaluation of uncertainty. So the sensitivity analysis is carried out on these 11 parameters. So these are the grade of concrete, the FCK value, the steel, yield strength of steel. This is the masonry prism strength, damping, width of column, depth of beam, the material density of concrete, material density of infill, or the light load that is coming from the infill, the imposed load of infill, self weight. This is the width of the strut in the ground floor. This is the width of the strut in the upper floor, and this is the strain, the compressive strain in the strut. So these 11 parameters we have considered in the analysis. So these are the mean values which are shown here. So if you remember initially I said that mean frames were considered. So in those frames only these mean values were used. No variation was used there. So these are the coefficient of variations that we consider in each of them. These are the standard deviations, and these are some of the references from where we have utilized these values. So we carried out nonlinear analysis, nonlinear time history analysis, considering those 7 different ground motions and 16 samples for each random variables. For each of these variables, we developed 16 samples. Okay, by considering this as mean value, this as the coefficient of variation, and these are the standard deviation. Right, so their values ranges from maybe 17 MPa to around 30 MPa, 32 MPa. So between them, we use 16 samples for FCK, similarly 16 samples for FY, and so on and so forth for all 7 ground motions. So around 2,600 nonlinear time history analysis were carried out, and I'm showing you those results here. Let us see how these input parameters, they change with respect to each other. So if I consider their variation as 100% total, so out of that you can see here that the variation in damping is maximum, which is 34%. This is input in uncertainty chart, right? The strain uncertainty is 19%. So when you can see here, the mean value is 0.0015, and here you have large coefficient of variation 0.43 and large standard deviation as well. Similarly, you consider the width of column only 1%. That is simple, because when we say that it is a 300 by 300 cross-section column, we generally don't expect that somebody will make 350 by 350 column. That is not acceptable. That generally doesn't happen. But instead of 300, we can get 305, right? 300 and maybe 310, maybe 303, 302. That is possible sometimes. So that variation is shown here, right? But material strain, there is a 19% variation. Width of strut, there is 18% variation. FM prime, 11% variation. So on and so forth. So we'll see what is the influence of variation in these input properties on the output of the structure. That is the study. That is the sensitivity study. So all the how many? Some 2,700 ground nonlinear time history analysis. So those results are actually compiled here in very simple, simplistic way, so that you understand in a very short time. So these are called radar charts. And what you see here, along the periphery, you have these 16 samples, right? So these are the samples of the random variables. Along this radial line, so when you go out from the center, you have the increase in the displacement. So these are the normalized displacements, so from 0 to 1, right? So we increase displacement when we go away. Okay. And these different colors, they represent these 7 ground motions. So 1, 2, 3, 4, 5, 6, 7. And these are the 7 ground motions. So these numbers here, they represent the coefficient of variation in beta C. BC, width of column. This is also BC, this is BC, but these are for 3 different frames. Bare frame, open ground story, and fully infilled. Here I'm showing the variation in depth of beam for 3 frames. Now it is very clear if you look at this figure, where is more scattering? The more scattered are the results, the more influencing those parameters are. So if you look here, there's not at all scattering here, right? Whatever you do, even if you change the depth of the beam, all 16 samples, you change the ground motions, you change the type of frame, it really does not matter much, because there is not much scattering except for in this fully infilled frame where there is a marginal scattering you can see. But in case of width of column, you change little bit and you get more scattering. That means the results are varying. And which results we are talking about? We are talking about the displacements. So for example, if you consider this open ground story frame for this earthquake, which is this one, this is Dutch earthquake. So for the Dutch earthquake, you can see when you change the samples, the results vary, right? For sample 1, this was the displacement, which was around 0.6 meters. When you use the 16th sample, the results become top, right? It is reaching here. So that is the kind of variation I'm talking about, right? So in all three, there's a huge variation. So simply BC is more important as far as input parameters are concerned, and DB is less important. That is the output. Similarly, you can see the variation in FCK here and FY. And obviously, you will again find that FCK variation is more important in case of this analysis. FY variation is not that important. They are important. It's not as bad as the depth of beam, but still comparatively FCK variation is more important because that is where the cracking starts. That is where the reduction in the stiffness starts. Right? So these are the kinds of analysis required to find out these results. Then the variation in damping, variation in the material density. Again, material density, you don't get much scattering compared to what you get in damping. So you see here how scattered are the results. So zeta is more important in case, particularly in case of full infill frames. The imposed load versus FM prime. Now obviously FM prime will be more important in case of fully infill frame, right? But the imposed load may not be that important, right? So even the width of strut also, the width of strut will be more important, and the FM prime will be more important. So what I'm showing you here is the imposed load for all three frames, bare frame, OGS, and FY, and FM prime for FY, width of strut for FY, and epsilon m strain for FY. Because this FM prime, the width of strut and strain in masonry they are not relevant in case of bare frame or even in case of OGS. So I'm just showing you results of full infill frame. And look at the variation in the results, huge variations. Right. So what if we change the type of analysis instead of this the radar charts? If you simply use the bar charts, do we get the similar kind of results for individual the important parameters and for different ground motions? So these are plotted for different ground motions, all 7. And out of 11 parameters, I'm just showing you here 7 important parameters. So these results are for the bare frames, and obviously you can observe yourself where are more variations in the normalized displacement. The more variations are in BC, the width of column, and FCK. That's all. Otherwise, very less variations are observed in all other input parameters. And I'm sorry, these are the output parameters. Change in the output parameters because of changes in the input uncertainty. For open ground story frame, similar results, BC and FCK. These are the changes. In some cases, the imposed load is also there, but not much compared to these two. In full infill frames, these values are not at all important. What is important is FM prime and the width of strut compared to all others. Right? So these are some common sense. We can say that this is perfectly all right, because in full infill frame, initially most of the lateral loads are resisted by the masonry infill. So therefore, the input uncertainty in FM prime and WS will be mostly governing the output of the system. Now, third type of analysis, the tornado diagram analysis, when we do. So based on these swing values, so these variations here in positive, negative, these are called the swing values. So based on these swing values, we can check the order of response sensitivity. Response is the displacement response. So we can check that response sensitivity to different random parameters of different frames. So we can see here the results are available for the bare frame, for the open ground story frame, and full infill frame. And if you look at bare frame, BC has the maximum response sensitivity, then followed by FCK and followed by zeta. OGS also, but for fully infilled, again, these are the different. So these are independent analysis carried out to validate whatever we get in one type of analysis. And the coefficient of variation in case of 3 different frames for all these 11 parameters are shown here. So this shows the comparison of sensitivity of response to different parameters. Again, for fully infilled frames, look at here. These are mostly governing the response. And finally, this Sobol's index, which gives you the variance-based sensitivity. Right, so there's a simple formula to calculate that global sensitivity index. And we again find that in case of bare frame, FCK, the variation in FCK is here, variation in Sobol index because of variation in FCK and BC. Similarly, in OGS, FCK and BC, and in case of fully infilled, this is FM prime and WS. So significant impact of variation in FCK and BC, and in some cases zeta on the response of bare frame and OGS frame. In infill frames, the variation in FM prime and WS hold the major position. So with the help of several independent type of sensitivity analysis, we have actually concluded this. So in the end, this figure I already showed you that these are the relative differences in the uncertainty of or the variation in the input parameters. Now let us see what is the uncertainty in the output considering these variations in the input. So this is response sensitivity chart. Now remember there's only 1% variation in the width of column as input, but because of that 1% variation you get 30% variation in the results in the output of bare frame, right? This is very important. Similarly, in the open ground story frame, you have 30%, 31% variation, which is the maximum variation. In FCK, there is a, because of a change in FCK, which is only 6% variation, we get 26% variation in the output in bare frame and OGS frame. And in case of fully infilled frame, the maximum variation comes coming from FM prime, 35%, and width of slit, 29%. BC is only 3%. FCK is only 3%. Doesn't matter. And some portion of zeta, but mostly it is FM prime and WS. Even if you look here, FM prime variation is 11%. And WS variation is 18%. Right? So this is the different kind of output quantities which are important for different types of frames. And another important point here is the magnitude of uncertainty in input parameters may not solely decide degree of their sensitivity in the output response. So what it means is that if you consider this zeta, which has 34% variation in the input parameter, it has only 12% variation in the output response sensitivity. Here it is 11%, and here it is again 11%. So that doesn't fit in a straight line, right? If this is more, that doesn't really mean that output sensitivity will also be more because of that. But even in 1% variation here gives you a huge variation here. Fine, so now we will use all these results in the uncertainty estimation to actually find out the fragility. So there are two basic sources of uncertainties. One is the aleatoric uncertainty, which comes from the record to record variability in ground motions. Like I said, every ground motion is different, and we can have the synthetic ground motions. We can deliberately change these ground motions by providing some uncertainty by some changes. So this is aleatoric uncertainty. And second is the epistemic uncertainty, which is coming from the inherent variability in the random system parameters, like all these 11 parameters that you have considered. So we again have to carry out a detailed nonlinear analysis to estimate this uncertainty. And this is a very simple equation proposed by Selick and Ellingwood. So it's SRSS actually. The total uncertainty is SRSS of this beta D, so uncertainty in demand, coming from the ground motions, uncertainty in capacity, coming from the system parameters, and uncertainty in modeling. So these are the three, and beta M is generally assumed to be 0.2. So no separate analysis was carried out for beta M, but we carried out analysis for beta DSI and beta C. And this is a very well-known log normal equation for estimation of seismic fragility, which is suggested in Hess's code. And using this equation, we can get the probability of accidents of a certain demand parameter. So that we'll discuss later. But just to show you what is the variation in the fragility when we vary the uncertainty. So when we vary the uncertainty from 0.1 to 1.2, we get so much of variation in the seismic fragility. Okay, so this is the seismic fragility is estimated as probability of accidents of a certain damage state, considering this the spectral displacement as the demand. So there's a huge variation. That is why we must understand for what level of uncertainty we have to plot this seismic fragility. So again, we use the same 7 ground motions, 16 different samples of these ground motions created by having the what you call the frequency dependent envelope curves for these ground motions. So we did that, and so total of 112 ground motions, and then we again changed the peak ground accelerations from 0.0 to 2.0. So there are 25 peak ground acceleration values for each of these ground motions that we considered, and we considered 3 different frames for each of these analysis, and finally we get 8,400 nonlinear time history analysis runs just to estimate what is the uncertainty in only the ground motion uncertainty. So these many analyses were carried out, and we used a probabilistic seismic demand model. This demand model was used to estimate this A and B value for a particular seismic intensity, which is PG. Okay, so we use this power law, and I'll not go into too much of detail here, but this is the kind of output that we get for different ground motions. So we get these, we estimate these A and B, and for each of that estimation, we get the R squared values, which is very high, near to 1 for all 3, for top level displacement and the ground level displacement that we calculated. And these are the uncertainty in responses due to ground motion variability. So aleatoric uncertainty we have tried to obtain. So this for the bare frame, top level, open ground story frame, fully infill frame. And similarly, the 3 frames for the ground level displacement. So this red dots, these are the combined uncertainty coming from all these ground motions, and these are the 7 curves for the individual ground motions, right? So standard deviations you can get from all these. And what are the values that you generally expect for the beta DSI that we'll discuss later? But from here you can say it is varying from maybe 1.5 to 3 for bare frame top level, and for OGS the variation is different. For fully infilled also the variation is different. Okay, so these are for yes. So if you look here now, the average uncertainty calculated from the samples of ground motion are mentioned here. So the combined average for bare frame is around 0.21. For open ground storage is 0.23. For fully infilled is 0.31. And for ground level, slightly different. We can compare them with the past results, and they're more or less matching, with the difference that these results did not, these past study was not carried out for the ground level displacement, which is more important. Okay, now mind you that this uncertainty is only the aleatoric uncertainty coming from the ground motion variability. Okay. So obviously the uncertainty obtained, they are not suggested in the literature as the EDP. Right? For ground level displacement as EDP is not suggested in the literature. Fine. So now how about the epistemic uncertainty? So for that we need to create a lot of models, right? We need to create a lot of data. Thousands and thousands of analysis were required to be carried out. We cannot do so many analysis because for aleatoric uncertainty we carried out more than 8,000 analysis. So you can imagine we need to carry out 40, 50,000 analysis for epistemic uncertainty. So we did not do that. Instead of that, we used some simulation sampling, which is called Latin hypercube sampling, which helps us to reduce the number of analysis, but without reducing the quality of the output. So these are some of the methods in generation of the data. So people have suggested many norms. So number of simulations, we carried out a lot of simulations just to see how many samples are required. And finally, we could find that by using the PSN and the Pearson coefficients, correlation coefficients, we came up with some simulations that are 25. So if we use the 25 simulations for individual ground motions, considering 3 different frames, we can get similar kind of output that we could get from thousands and thousands of analysis. So finally, we use 3 frames, 25 models, and 30 PGA, peak ground acceleration. Now these 25 models, what we did, we varied the 11 parameters systematically using this Latin hypercube sampling, right? And finally, 2,250 nonlinear time history analysis were carried out. And this is how we obtained this beta C, in the uncertainty in the capacity. So you can see it depends on PGA. So when we increase the PGA, uncertainty increases. There is a more variation in the uncertainty, right? So for given PGA, maximum uncertainty is there in case of fully infinite frame, which is obvious because they are more related to the or not related, but they're more sensitive to the lateral displacement. So then finally, we club these together and obtained the total uncertainty. So here is the uncertainty in capacity, aleatoric uncertainty, and here is the uncertainty in the demand. Sorry, this is epistemic and this is aleatoric uncertainty, and this is the total uncertainty coming from and square root of sum of squares of beta C, beta D, and beta M, which was 0.2. So finally, what we get is the beta, the uncertainty value coming from the codes as well. So some codes are available for reinforced concrete and reinforced concrete URM structures. Limited numbers are available given in the code. So median values and the beta values. So what we get is 0.5. This is the present study, right? So 0.5, which is much different from what is specified in the code. This is not the Indian code. This is the US code, IBC. And for infill frames also, we get different results. Right, so uncertainty and collapse increases with increasing number of stories. That was also observed, that can also be observed from here. And if we take these uncertainties and plot the fragility values, we get, of course, we will get different fragilities for different uncertainties. So we are plotting them for 3 different types of frames specified in this IBC. For slight, moderate, extreme, and complete conditions. So this is reinforced concrete, infill buildings, this is bare frame buildings. Right? So we cannot simply use the category given in that code for our category, for our type of building. Right? So this RCC1 predicts almost similar fragility as the bare frame. Okay, so we can compare these bare frame results, but not the fully infilled or the OGS frame results. Right, so then final part of the study is estimation of seismic fragility. So what we have done, we consider the buildings, we use the nonlinear static and the nonlinear dynamic analysis, use the response spectrum, vary the material properties, vary the ground motions, combine them, and we get the responses using the two methods, nonlinear dynamic and nonlinear static. And finally, we obtain the seismic fragility considering the local or global EDPs, considering the sensitivity, and considering the uncertainties. So this is what is required to be done if we have to do complete fragility assessment. But then people generally don't do this analysis. They assume some uncertainties, they consider some sensitivity, they can directly obtain the seismic fragility. Now, initially, if you remember, I said that I'm varying the openings in the fully infilled frames as well, and in the open ground story frames as well. So here, the fragility curves, they show the influence of openings as well. So for 4 different damage states, slight, moderate, extreme, and complete, you have 3 different frames. And here I'm not considering any opening. These are for 0% opening. These are for 50% openings. And you can yourself see what is the variation in these 2 curves. So if you have these openings, the seismic vulnerability or the fragility of the fully infilled frame, it slightly comes down, right? But otherwise, there is no change in the open ground story frame. That fragility remains the same. Even the bare frame doesn't matter. So that is one important output, that openings in the upper floors doesn't really change the seismic fragility of the open ground story buildings. And here we use the spectral displacement, right, as EDP. Here we are using the peak ground acceleration. So similar story. It doesn't really matter whether there is opening or not. The open ground story buildings, they remain more fragile for all cases, damage states. And here I'm showing you the fragility contours, similar results, but in slightly different way. So these are for slight, moderate, extreme, and complete. For this combination of opening and PGA, is 50% opening and PGA, is 0% opening and different PGA, right? So here I'm changing the number of bays on the x-axis, 1 to 6. On the y-axis, I'm showing you the number of stories. And these are the fragility contours. So what we get here is that for a given PGA and number of story, for example, if you consider only this chart here, the fragility increases with number of bays. Obviously, you have higher stability, higher fragility when the number of bays are increasing. And similarly, the fragility also increases with number of stories. So if you fix the number of bays and you increase the number of stories, you have more fragility. And for given PGA, number of bays and number of stories, fragility decreases slightly with openings. So if you compare this with this, there's a slight reduction in the fragility. And here I'm again comparing the nonlinear static analysis results with the nonlinear dynamic analysis results, and we get more or less similar kinds of output, that the open ground story frames are the most vulnerable frames, even if we provide openings in the upper floors, right? And so more or less the static procedures, they overestimate the fragility, and at the higher peak ground acceleration, the fragility of fully infilled frames becomes similar to open ground story frames. And this is, we have already observed that for high PGA, we have more or less they remain same. So these are the final conclusions of the talk today. That the lateral load behavior of open ground story frame does not depend on the openings in the infill walls, right? But the fully infilled frames, they depend. Okay, so that means the ground story infill plays a significant role in the lateral load resistance. For regular frame, we can use a conventional engineering demand parameter. But for irregular frames, we have to use the component level engineering demand parameter for estimation of realistic damage and fragility. The component level EDP is also required for regular fully infilled frames that can become irregular when we have failure of the ground floor inputs. The sensitivity analysis shows that the response of the bare frame and the OGS frame is highly sensitive to BC, which is width of column, and FCK. Similarly, for full infill frame, the most sensitivity come from the prism strength of masonry and width of equivalent diagonal strut. We also calculated the total uncertainty by considering aleatoric, epistemic, and modeling uncertainties. And we observe that our codes are not adequate as of now to tell us proper uncertainty that can be considered in the analysis. And finally, the seismic fragility we obtained using simplistic nonlinear static analysis. It is found to be more conservative than that obtained using nonlinear dynamic analysis. So even if we don't carry out this nonlinear dynamic analysis, which are more complex to be carried out, we can still use this nonlinear static analysis, pushover analysis procedures properly, systematically, and we can still get the seismic fragility with reasonable safety margins. So the study that we discussed today, all these results were the PhD thesis of Dr. Trishna Chaudhary, who is presently working at Thapar University in Patiala. So I really wish to thank her for the excellent work that she carried out during her PhD. And thank you everybody for patiently listening to this boring lecture. I hope I was clear. If there are any questions, feel free to ask.
Sir, first of all, the lecture was not at all boring. It was very, very informative and interesting.
Thank you.
Participants, do you want to ask something? You can mail us also. Sir, I have one question, sir.
Yes.
Actually, in SAP, when we used to apply times tree, it is very difficult to get the result because computational time is very much there. Around we are getting more than 11 hours, 12 hours, and sometimes 24 hours. Although we'll try to modify it from MDF to SDF, sir. So, is there any other software other than SAP in which we can apply times tree to reduce the computational time?
There are many softwares actually which can be used, but you see, almost every software will take time in carrying out the nonlinear time history analysis because it is complex. Right? There are so many input quantities, so many output quantities, and the material degradation. So it takes time actually. OpenSeas is a much simpler software. You can try using that, but then I personally feel, and I always use SAP, because OpenSeas you have to generate model somewhere else, and then it's more of a non-GUI based approach. But SAP, you get the feel of the structure. It's much simpler actually. You need to have a good server or a very good workstation to carry out this.
Sir, any other site other than USGS where we can get time series records, particularly for Indian earthquakes?
Now there are many actually. I don't remember. Cosmos was one, and IT Roorkee has this very good deposition of ground motion records. So I generally personally I have stopped looking for these earthquake motions because students mostly do this now. But I remember Cosmos. I used to download from Cosmos, but I'm not sure whether it is now today. But there are many nowadays. Large number of repositories are there from where you can get it free.
Sir, particularly for masonry point of view, what will be the interval? Means ground G value interval.
I have not understood what kind of interval.
Sir, actually for RC frame with infill, we have taken an interval of 0.05 G. So for masonry, do we need to change or we can use the same interval?
See, you don't have to carry out same analysis again and again. right? You can cite some of these results that this was already done and I'm considering this value from these. So that is perfectly okay. I mean, but if you want to carry out yourself, then you have to do very fine analysis considering finer intervals. That is why it was done. But for Indian masonry conditions, because we considered right from very weak to strong masonry. There's no need to repeat those analyses. Use those analysis results and carry out something else. You take it forward.
Sir, means when we are considering a masonry building, then also we can take these intervals.
That is what you see. You don't have to consider these intervals all the time. Let us say you have 10 or 11 ground motion records available with you. You use those original ground motions itself. Okay, and then you cite this study. These are all published results in good journals, excellent journal publications are there. You cite this that this study shows that variation is this much, right? And then therefore I'm using these 11 ground motions or 13 ground motions. Some codes say you use 17 ground motions, but you must use at least 7 to 11 ground motions, different types of ground motions. So pay some attention to searching for different types of ground motions. Use the original ground motion. If you want, you vary the PGA slightly, maybe not from 0.05, but you normalize it to 1G,
Yes.
and maybe from 0.3 to 0.1, 0.3 to 0.6G, you can use that.
Any other questions? So you can mail us. We will give the questions to sir, and after sir response, we will mail to you again. Thank you very much, sir.
Thank you. Thank you for giving me this opportunity. All the best.
Thank you, sir.
Thank you so much, sir, for a wonderful session. I thank Kaushik, sir, on behalf of the Civil Engineering Department at IPS Academy. We are honored and privileged to have an interaction with you, sir. And we thank you that you could manage time from a busy schedule and enlighten us over the important topic of this geotechnical earthquake engineering, especially the different types of ground motions which you specified in the lecture were very important for us. Thank you so much, sir.
Thank you, Dr. Jagwani. Thank you so much.
Thank you, sir.
Okay, bye bye.
Bye. Sir.
ज्वाइन है कि नहीं
So the next session is scheduled in at 11:30 a.m. We request the participants to have a break of 5 minutes and join us soon.